All right, let's dive in and unfold one of the biggest mysteries in all of biology. We're talking about proteins, the tiny, incredible machines that basically run our entire bodies. How on earth do they twist themselves into the perfect shapes to do all their amazing jobs? It's a journey to the very foundation of life itself.
It really all comes down to this one question. You see, every protein starts out as just a simple, floppy chain of amino acids, kind of like a long string of beads. But for it to do anything useful, it has to fold into an unbelievably precise 3D shape. So, how did this flimsy chain figure out exactly how to bend, twist, and fold? Well, here's the secret. It's not random at all, not even a little bit. It's a super carefully orchestrated process, and it starts with these simple, local folding patterns. We call these first folds secondary structures, and they are the absolute building blocks for the final masterpiece.
So, let's kick things off with the most famous structure of them all, the alpha helix. This beautiful spiral was actually predicted way back in 1951 by the amazing duo of Linus Pauling and Robert Corey. And what's really mind-blowing is that they figured it out years before we had the tech to actually see a whole protein.
So what does it look like? Well, just picture a perfect spiral staircase. The main part of the protein chain, the backbone, just winds itself tightly around a central point. This is basically nature's favorite way to pack a piece of the chain into a really compact and stable shape.
So, what's the glue that holds this whole spiral together? The secret is a huge network of something called hydrogen bonds. Now, each one of these bonds is actually pretty weak on its own, but when you get a whole bunch of them together, they act like countless tiny magnets, creating a structure that's incredibly stable and rigid.
And check this out. There's a really precise and beautiful pattern to it. A hydrogen bond forms between one amino acid and another one that's exactly 4 spots down the chain. This pattern just repeats and repeats, which basically staples each turn of the helix to the next one. It's what locks in that perfect spiral shape.
Now, if we could shrink down and look right down the barrel of this helix, you'd see something brilliant. See how all the side chains, those are the R groups that make each amino acid unique, are all pointing outwards, away from the center? This is so important because it leaves them exposed and ready to interact with other molecules, which is literally how proteins get their jobs done.
And here's a really cool fact. Pretty much every single alpha helix you'll find in nature is right-handed. You can actually try this yourself right now. Just point your right thumb up and curl your fingers. The helix spirals in the exact same direction as your fingers. It's a simple rule of thumb, literally.
But you know, nature loves to have options. So the alpha helix isn't the only tool in the protein's toolkit. Pauling and Corey also figured out a second, totally different structure, the beta-pleated sheet.
And wow, the difference between these two is just striking. While the alpha helix is this tight little coil, the beta sheet is made of these long, stretched-out, zigzagging strands. And here's the really big difference. A helix bonds to itself, right? But a beta sheet forms its hydrogen bonds between these separate strands, linking them all together side by side.
Now, these beta sheets come in 2 main flavors. The first one is called anti-parallel. This is where the connected strands are running in opposite directions. Just imagine 2 lanes of traffic on a highway, one going north, the other going south. This setup allows for some really straight, really stable hydrogen bonds.
The other flavor is the parallel beta sheet. And as you can probably guess, here the strands are all running in the same direction, kind of like multiple lanes on a one-way street. Because of this alignment, the hydrogen bonds that connect them are a little bit angled, a little bit bent, which makes this structure just a tiny bit less stable than the antiparallel version.
Okay, so we've got helices and we've got sheets. But what actually decides which structure a piece of a protein is going to form? Well, like I said, it is not random at all. The specific sequence of amino acids has all the information it needs. It's basically a set of rules for folding. For an alpha helix to actually form and be stable, this incredibly complex balancing act has to happen. It's not just one thing, it's a whole bunch of factors all at once. From how bulky the side chains are, to whether they're positively or negatively charged, even a tiny electric field along the helix itself plays a part. It's like a delicate chemical negotiation happening at every single step.
So, in this negotiation, 2 amino acids are famous for being troublemakers. We call them the helix breakers. Proline, because of its unique ring shape, actually forces a sharp, rigid kink into the protein's backbone, which just messes up the whole spiral. Then there's glycine. It has the opposite problem. It's too flexible, too wobbly, and it would rather be in other kinds of shapes.
But just as some amino acids can break a helix, others can make it stronger. Because of the spiral shape, amino acids that are a few spots apart on the chain actually end up right next to each other in 3D space. This allows them to form powerful bonds, like this one right here, an ion pair between a negative and a positive side chain. It acts like a tiny molecular clamp, locking that helix firmly in place.
So we have these rigid, organized pieces, helices and sheets, but a protein isn't just one long helix or one giant sheet, right? It's made up of a bunch of these elements, and to form a compact, functional shape, they all need to be connected together.
And that is where things like the beta turn come into play. These are tight, 180-degree U-turns that let the protein chain literally fold back on itself. And guess which amino acids are perfect for making these sharp little bends? Yep, our old friends, glycine and proline. The very helix breakers we just talked about, well, they find their true purpose right here, connecting the big, rigid structures together. So you see, putting together these alpha helices and beta sheets is the absolute first, crucial step in turning a simple chain into a working machine. These structures are the foundation that the entire protein is built on. It just shows how incredibly important these initial folds are. And it leaves us with one final, pretty serious question. With a process this complex and this delicate, what happens when just one tiny step goes wrong?